Okay, welcome to my second presentation on trajectory analysis, and this one is on simplifying trajectories. So let me just start by showing you somewhat arbitrary data set I recently worked on. So these are gulls, migrating gulls, and so this is a data set, and you see, okay, you cannot distinguish points. Even if you kind of zoom into a small part, then still on that small part, I mean, there are so many points that you cannot really distinguish individual points. And this is not even a very dense data set. So typically the data sets that we need to deal with are very large. And then if on the other side we look at the type of algorithms that we want to run on these data sets, so let me just put up a few examples which so similarity we saw yesterday, and the other analysis tasks we'll see in the upcoming days. Then if you look at these running times, so similarity is quadratic, the segmentation, so breaking trajectories into pieces, at least in general, is also quadratic. More complex tasks, cubic, then it's clear that we will not be able to perform these analysis tasks directly, at least not with these algorithms, on the data that I just showed you. So what we need is somewhat smaller data to apply these algorithms, and very often there is a lot of amount of data that we can essentially ignore and still get a good approximation of our trajectories. So in this example, all of these data points in between here, even if I drop them, and even if I drop this one here, okay, here I kept one, then this is a sufficiently good approximation of this original one. Also, even if we want to take into account time, so here's another example. So if I have this trajectory, and maybe it's important that I stayed here for a long time, then I can simply maybe keep two of the points here, the first one and the last one, and then also the temporal information is maintained well. So trajectory simplification is a problem we want to look at today. Let me just come back once briefly to what assumptions we are making about our input. So we were looking at trajectories from this perspective, that we have these data points and we line them up using essentially getting a polygonal curve. There are some assumptions we do not want to make. So often assumptions like regular that you have uniform sampling is assumed, so we will not want to make that assumption. We will not want to make any assumptions about missing data, and so we don't know anything about the trajectory in between. So essentially what the question that we need to be able to address here is again a question like if I want to have a trajectory that represents another one, then we end up with this question of how much does one deviate from the other, and therefore we want to, so what we ideally want to have is something continuous, because so in particular, so what happens if you do simplification? So yesterday we saw, for instance, a discrete Fauché distance, which is also used for simplification sometimes. But if you use a discrete measure, then you end up with problems that if A would have been the simplification of B, then suddenly you get very large distances, although A is fairly close. Yeah, so if one trajectory has much fewer data than the other one, then these discrete measures run into problems. So what we essentially want to have is a line simplification algorithm, and most of what I'm going to talk about today will actually be line simplification, simply because it's the easiest version, but I will also note how to then later incorporate time. But so before I start with line simplification, I want to, as a kind of word of warning, talk a little bit about why that does not solve the problem with time necessarily. So if this is my original trajectory, let's say, then line simplification, as we will look at it today, will give me this simplification. But now this, if this is, let's say this was uniform sampling, so here I was moving very slow and then very fast, then this information about the speed is not represented here. So if we assume this is uniform, then the speed information got lost here. And what we would actually like to have is we would actually like to have this point within the simplification so that we still know, okay, this we did very slowly and then this we did fast. Now, simplification should be essentially a trajectory with very few vertices, which is close, which is very similar to our original trajectory, or stated differently, which introduces a small error. So in that regard, we'll have to think about what kind of error do we want to allow. And we'll be looking at this setting of maximum error. So given an input trajectory, I will want to find a simplified trajectory such that at any point in time the maximum distance from the trajectory to the simplification is small. So that is if I really want to keep the time in. And that then would enforce this variant here. Because again, if you would look at this one, and if you think about this simplification and where I am after 5 minutes, then that would actually be somewhere here. So that is not that a line simplification does not preserve speed in the trajectory data. Then, so we can look at we could also look at, for instance, error in velocity. So now I was discussing speed. We could also look at error in velocity. So that would be speed and heading of the trajectory. And you can also look at combinations of that. So, but now let me, after saying all of this about how to incorporate time, speed, and so on, I will actually want to start with this very simple version of line simplification and solve that first. Because all of this, so for instance, velocity, we can, or no, let's say speed, we can include by simply adding time as a dimension afterwards. So for now, we want to simply think about this in terms of spatial similarity. And as I said, time we could in doubt put into another dimension. And the standard algorithms for this, I would argue, are probably these first two, so the Douglas-Peucker, or also Raman-Douglas-Peucker heuristic, which is used a lot in geographic information science. From the computational geometry perspective, this framework by Imairi is kind of considered more as a direction to go. But this is this is a quadratic time algorithm, or, at least in its fast version, which is still not very fast. So I also want to discuss this algorithm by Agarwal et al., which is an approximation for what we get here, but will run in near linear time. Okay, so those are the algorithms I want to discuss. Let's start with the Douglas-Peucker algorithm. So this is very frequently used in GIS. Its advantage is that it's very simple to implement, and okay, at least the claim is that it works well in practice. So it seems that people are at least happy with what they get with this algorithm. The idea is very simple. We have a curve, polygonal curve, which starts and ends somewhere. Now we measure the distance. So we now, essentially the question is this curve sufficiently close to this line segment so to simply replace this curve by this line segment. For this we measure the largest distance to the line segment, that would be in this point here. And then we have some kind of distance threshold, this epsilon. And if this distance is larger than epsilon, we say no, this is not close enough. And then we curse on the two subproblems, taking the furthest point and trying to replace this part of the curve by this line segment and this part of the curve by this line segment. So the Douglas-Peucker algorithm is a recursive algorithm. Let me show it to you in a somewhat larger example. So let's say this is the curve we want to simplify. The first question would be, okay, can we simply simplify it by one line segment? This is the largest distance to the line segment along the curve. Let's say that is larger than epsilon. Then I will recursively find a simplification for the part from here to here and from here to there. So now the question is this a sufficiently good approximation of this part of the curve? If yes, good. In my case, I say no, and this is the reason why not. This is now the point furthest from this line segment. So I continue my recursion and so on. So and eventually this would be the simplification we end up with. Other questions so far?
So
yes?
Douglas-Peucker, the error is not changing monotonically, right? So the error might increase and then decrease and increase again.
Yes, yeah. So there's not so much in terms of theory that you can say about this algorithm, but I'm showing it because it's used so frequently. In particular also on trajectory data. Yes?
I know that the algorithm gives us a unique solution. But,
Yeah.
But is it possible that we can find another solution for this sample that we have the distance minimum less than this one, but the number of with less number of the points.
So your question is essentially whether there's a
With this minimum, is it optimal?
no, it's not optimal, exactly. So that was your question, and no, it's not optimal. I will also show an example which shows that it's not optimal. Yes?
Can we retrieve our trajectory from this algorithm, or our data points are lost after simplification?
I mean, I guess that depends on what you do with your data. I mean, if you just store the simplification, then this is lost.
I mean, for compression, sometimes
Yeah.
we want to retrieve our trajectory.
Mm-hmm.
Is it possible from this algorithm to retrieve our trajectory?
So this algorithm as such has no mechanism to kind of store this information. So this is not, I guess your question is whether this would be lossless compression. No. We simply forget about everything that is here. It's an interesting question, actually. I mean, I don't think that in terms of this type of data, there's much kind of... I'm not aware, actually, of work that kind of tries to do lossless compression. Okay, so that is this algorithm. Let me say a little bit about the time complexity. So we find the vertex that is farthest, so that will take linear time, and then we recurse on two subproblems. So if I'm looking at the subtrajectory from I to j, testing whether the shortcut works takes, as I said, linear time in the length of this setting. Then I have this recursion, and in the worst case, what might happen is that if immediately the second point is already the furthest, then this is a very unbalanced split. So maybe I'm just splitting off a very small part of the trajectory, and then this is a quadratic time algorithm. And there are improvements in computational geometry. Yes?
I don't have a question. I guess it just should work for the trajectories which they don't have certain percent. Because in that case, then I guess that the value of the epsilon will change of the solution very... I mean, for different value of epsilon, we may just have to change some parts, and then, I don't know, I mean, I'm just thinking that this method shouldn't work for some kind of set intersection trajectory. Does it work?
So it depends on. So in principle, you can simply use it for self-intersecting trajectories. Yes. You might. Maybe your question is also related to the output. Whether the simplification as such, for instance, might also be self-intersecting. Is that? And then you can actually look at the question of, can you get a simplification that is non-self-intersecting? So that this work by, I think, Jack Snowing that looked at that question. Is that?
Yes, I think about it a bit more. Then I'll ask you again. And in your time complexity, you don't have something as epsilon, but I guess that for a very big epsilon, then you would just simplify your big trajectory just to a line segment.
Yes.
And whatever you want.
Yeah.
So, but you don't have something as epsilon in your time complexity.
No.
It's just quadratic.
If you would want to put epsilon here in terms of the time complexity, then you would want to put it into relation to some other quantity. In principle, right now epsilon is just a number, so I can.
I read that it's big or notation, but my question was that where is the epsilon? Here in the but my guess was that yes, I know, but I'm just thinking that.
So I understand the question. If you could try to relate epsilon to some kind of quantity of the trajectory and then integrate that with the running time somehow, but that is not done.
I can imagine that for epsilon equals to 0, we will give this running time. I can imagine that when we really want to simplify a trajectory to itself, then this is the worst case running time. I can imagine that. But my question was that, okay, for a very big epsilon, then. Okay, I get the point.
Yeah. I think there could be interesting questions in that direction, but I think one would have to first formulate the specific question to look at, and maybe not for this algorithm, but more kind of maybe the question of designing an algorithm for whatever you're now going to define. Good. So, once more about this algorithm, it runs in quadratic time. Of course. Somewhat, I'm not sure whether realistic is the right term, but not unlikely somehow the split will be more in the middle, and then the running time is of hopefully on many data sets closer to n log n. There's also nice theoretical work on this, so it can actually be computed in n log n time, and for non-self-intersecting curves in n log star n time. And the idea there is some kind of using dynamic convex hulls. But so we have the issue with running time. That is essentially solved if you use computational geometry. But there's still the issue with the complexity of the simplification. And if we we'll now switch to the next algorithm, but my motivation for this is the following example. So if this is my input trajectory, so it goes up here, wiggles, goes back, and this is my epsilon, then what the Douglas-Peucker algorithm will do, it will look at this segment here, it will find the point that is furthest here, and now recurves. So this part is already fine. But in this part, now the furthest is here, and then it's there, and then it's here, and so the result, the simplification will be this, which has complexity n-1. While the simplification, an optimal simplification, if we restrict us to vertices here even, is going from here to this vertex here, and then just moving through. So there can be a huge difference between an optimal segmentation, simplification, and what Douglas-Peucker gives you. So therefore, the next algorithm I'd like to show you is this algorithm, or it's actually the framework by Imairi, and then the algorithm is There's also the algorithm by Chin and Chan. That aims at, given an epsilon, finding the minimum number of links. Or you can also ask the question the other way around, but given a bound on the number of edges that you want to use in simplification, find the corresponding epsilon. So there's these two questions always. You can either phrase it in terms of, I want to minimize the number of vertices, then epsilon is given, or you want to minimize epsilon, then the number of vertices is given. And as we also saw in the example of the Fauché distance yesterday, there we solved the decision problem and then used some kind of binary search. And here it's similar. So most often this min vertex simplification given epsilon is the one that is considered. And if we then want to do min epsilon simplification, you here simply do a binary search over values of epsilon. And then you apply this algorithm, see how many vertices you get, and depending on that, either increase or decrease the epsilon. So another important distinction in simplification, which I so far kind of only mentioned implicitly, is there's an important distinction of whether you only use vertices of the input or not. So whether you're asking for any curve of a given complexity or with a bound at most epsilon, which is closed, or a curve that which as vertices uses the vertices of the input. And for most of the time, I will be focusing, or essentially for nearly all of the time, on the case where the vertices are part of the input. And then the most natural setting also is that if I have two consecutive vertices in my simplification, they should also represent the part of the original trajectory that is between those two vertices. So actually more recently there's also kind of the other, you could say other variant has been considered where you restrict to the vertices of the input but do not restrict that segment represents the part in between. And I'll say a tiny bit about that at the very end. But the setting that we have is the simplification should use vertices of the input, and the segments should represent the part of the trajectory of the input that is between those two vertices. And for this setting, there is this framework by Imairi, and the conceptual idea is very simple. So what we're going to do is, this is now maybe my input trajectory. Now I'm going to build a graph on the vertices of the input trajectory, and then I'll add an edge if and only if the corresponding segment is close enough to whatever is in between. So this could be my graph. So now for instance, here this segment represents the part from here to here. And let's say this part is similar enough to this segment, then that's why I'm adding this edge to my graph. But for instance, this pair of vertices, I do not add the edge because this vertex is somewhat too far away, or you could say this curve is too dissimilar from this, simply taking that segment. So I'm building this graph by simply for any pair of vertices deciding is the corresponding sub-curve or sub-trajectory close enough to that segment. And then if we have that graph, we can simply search for a min-link path from start to end. So in this example, that might be this here. And this is then our optimal simplification for the given epsilon. The bottleneck in this algorithm is finding all of these shortcuts. So finding all of these segments that are valid, could be valid in a simplification. Because we will always need to kind of test distances, and if we do that a quadratic number of times, In particular, if we now test long edges, that might be very expensive. And now we also have to decide on a distance measure to use for the subtrajectory. So what I'm now going to use in the next slides, because that is what traditionally has been used, is to take the Hausdorff distance from the segment to this subcurve. So last time I told you, okay, Hausdorff distance is not a good idea, and you can also do this with Fauché distance. Here, Hausdorff distance is often not quite as bad, because at least one of the curves is very simple. So even if what you're representing goes, I mean, essentially Hausdorff distance means you have to stay within this region around that epsilon. Yeah, let's say it is epsilon, you have to stay within this region. Then the subtrajectory might go back and forth a lot before ending up here, but it's still arguably fairly similar to that segment. But if you don't agree, you should use you can also use a different distance measure, and I will talk about that later. So I now have to test whether the vertices in between are close enough to that segment. This one maybe is not close enough, so I don't add that edge. This one, the curve in between has these two vertices. Those are close enough, so I add the edge. And this one is too far, so I do not add the edge, and so on. And now if I already look at all shortcuts from the first to any other vertex, you see that in terms of number of tests, this gets more and more complex, because now for this edge, I will have to test all of these vertices in between and determine the largest distance, and see that in this case it is too far away to actually use that edge. And so on. So these would be all tests from here, and then we would also have to do all tests from here, here, and in this way find all possible options. Okay. So that are all the tests I would have to do in this situation. Now, after having built this graph, computing the shortest path is simply a breadth first search. So that is fast. Now, let's have a look at the running time of this algorithm. So if I use Hausdorff distance and want to find all possible shortcuts, then that means I have a quadratic number of shortcuts, and the test that I have to do for a given shortcut is I have to test everything in between. So this is essentially linear in the number of points that are in between. So that will give me overall a cubic running time. So I have a quadratic number of possibilities. I have to test up to a linear number of vertices per shortcut. So this overall is cubic time to build this graph. And then this graph might have quadratic complexity. So then the breadth first search simply takes quadratic time. This can be improved to overall quadratic time, and that's what I want to show you next, the idea of how to do this faster. And the idea is to reuse information. So you tested for shortcuts. So let's say I started here and tested whether there's a shortcut to here, and let's say there was a shortcut. Then I'm going to reuse the information that I used to test this to also do the test up to here. And so let me give this by an example down here. So what I essentially need to know for this edge to be a valid shortcut is, okay, this vertex should have distance at most epsilon to this edge, which formulated differently means that if I take an epsilon disk around this vertex, it should be stabbed by this line segment. And now, if I want to now test the next edge, so up to here, then, okay, I draw the epsilon disk around this, and I will have to test whether this one stabs this epsilon disk and this epsilon disk. In this example, it's not the case, so this would not be a valid shortcut. But note, so this is not a kind of monotone property. So we will have to continue a test, but now next what we want to do is look at the epsilon disk here also and test whether this edge stabs all of these three disks, which it does. So this again is a valid shortcut. Then we'll continue adding this disk. The question is, do we stab all of these disks, which is not the case here, so it's not a valid shortcut, and so on. And eventually we'll end up in a situation where, if you look at this case here, so this disk is completely below this line. This disk is completely above this line. So at this case, if you start from here, it will not be possible. So we now fix this as a starting point, and we do all tests for the vertices that come next. At this point, I know that whatever comes next, no matter where it is, I will not be able to stab all the disks, because if another vertex is above this line, I will not be able to stab this disk. If a new vertex is below this line, I will not be able to stab this disk. But we can make this, so this is just an observation that at this point we can stop, but we can do this analysis a bit more carefully and maintain essentially the information of where may a vertex lie, so that I can still stab all the disks that are intermediate. So what we're now going to use is that a shortcut is feasible if it intersects all of those epsilon disks. And that means that the ways from, we want to look at the way starting at pi and going to pj, and that should stab all the disks in between. And then I have to go also from pj to pi and see that the way in this direction stabs all of the disks in between. Okay, and why did I do this reformulation? Or let's first see what this means in terms of the line segment. So what we essentially want to have is that this line segment stabs all of the disks in between. And I now just rephrase it in terms of, if I start here and shoot a ray in this direction, it will intersect all of the disks. And if I start here and shoot a ray in this direction, it should intersect all the disks. And the reason, yes?
Excuse me, for measuring the distance between two vertices, you don't consider the time dimension here.
Yes.
If you change this one, this algorithm to epsilon ball and sorting 3-dimensional space, then I think maybe
Yes.
we can get better results, yeah?
Yeah, indeed. So I'm now explaining the 2D result, but if you want to incorporate time, you do exactly what you just said. You add time as a third dimension, and then you have to think about how to integrate time. So you can do it with balls, but it might be the case that actually in your 3-dimensional space, you still want to consider disks. So I will actually come to it at the end, but now since you asked, so I have my time here. I have my trajectory that evolves over time. And now, depending on how you define your distance measure, which now includes space and time, you could do what you just said, that you place disks around here and you want to stab the disks. If you think of it more in terms of, at this corresponding point in time, I want to be close to this point, you might rather use just a 2-dimensional disk, but in this layer of time here. But it depends on how you want to integrate time. But certainly, so this is then with time, and I'm now kind of starting with the easier version of without time. Yes. And once more, okay, where were I? What I was saying was, I want to know for a segment, does it stab all the disks in between? And I said, I'm now replacing this by the test that I'm going to test whether this way intersects all of these disks, and whether this way intersects all of the disks. And if I can test those two efficiently, I know whether I should use this shortcut or not. Because now I can use the following algorithm, and this now starts at a vertex I. So now I'm going to start at this vertex, and the test that I'm executing is I want to test whether up to some j I'm intersecting all of the disks. And the way I do this, I maintain a wedge of possible directions starting at I, which are valid directions for intersecting the disks. So initially all directions are valid, and now starting with j being I plus 1, so I start at the next vertex. What I'm going to do is I'm going to intersect my wedge with, so initially everything is my wedge. Now I'm going to intersect it with the directions, with all of the directions where if I have a ray into this direction, it still stabs this ball. And now for the next vertex, I will have to see for the next vertex whether this is a valid shortcut. I now only have to check, is it within this blue area? And then to prepare for the even next vertex, what I'm going to do, so this one is in the blue area, I have the shortcut. But now I'm taking the epsilon ball here. This again defines a wedge, which I'm now going to intersect with my previously computed wedge. So this is now the intersection which I keep. And I continue from there. So now for the next one I test, is it in the wedge? It is. So this is a valid shortcut. Sorry, this is the next one. This is outside, so it should not be valid, yes. But still I continue drawing the disk. This gives me again a wedge. I intersect it with my previous wedge. This one now is inside, so I have a valid shortcut. I draw my disk. The wedge intersect. The next one is outside, so I do not have a shortcut. I draw the disk, a wedge, intersect. Now the intersection is empty, so I know at this point I can stop. And this is, I mean, you can do it on these disks directly, but you can essentially, it's a one-dimensional problem because you're intersecting ranges of angles, you could say. And as such, you can do all of these updates in constant time, which means that overall now, if you look at this algorithm, if every update just takes constant time and then every test takes constant time, then all of the tests starting at this vertex, I can now do overall in linear time, which is a large improvement to spending essentially linear time on each of the tests.
So
yes?
this problem can be somehow replaced in terms of the interval graph of this affiliation, where you count this one dimension. So by the intervals, I mean just the intervals are considered as the vertices of a graph, and they are adjacent and only if they have intersection. So maybe link means that the three intervals are mutually intersected, and so.
The key question is whether there is a mutual intersection.
Yes,
so
it's reflected in this graph, right?
Yeah, so that's reflected in that graph. So it could be phrased in those terms.
So perhaps this algorithm would be replaced in terms of something like this. I don't know at the moment, but maybe finding something in that particular object associated.
Yes, so I don't immediately see what the advantages we would get from that, but maybe if we look for something different in such a graph, maybe that gives an interesting variant. I would have to think about that. Okay, so that's in my theory. And now this runs in quadratic time because we spend linear time per vertex to do a test like this. Then we can also do all of these tests in the other direction. And then I have ways in both directions. And then I take an edge in the shortcut graph if and only if the test for both of the ways was successful. And overall, I spend a quadratic number of time. This was for the Hausdorff distance. So if I want to do it for the Fouché distance, then I can use exactly the same framework, but this improvement that I just showed you, that was special to the Hausdorff distance. So what I will now have to do is I have to test for segments whether the Fouché distance to the subcurve is small. And this now can be done in, that is then again back to the original framework, but linear amount of time per test. So that is then cubic time. So if you want to use a Fouché distance, here it comes at this cost of an extra linear factor. So far, so what did I show you so far? Two algorithms. The Douglas-Peucker algorithm, quadratic time, simple and fast in practice, but the output has no guarantee. Imai, which with this improvement, which I showed you, which is by Chan and Chin, takes quadratic time, and that actually is optimal in the sense as we defined it. So both of the algorithms that I showed you used Hausdorff distance, and if we want to use Fouché distance, it gets very slow. So the natural question is, can we get something faster using the Fouché distance? And at least in terms of approximation, there is a very nice algorithm, and also actually a very simple algorithm, which runs in n log n time, and it approximates. So the approximation is in terms of, so you see this is now as a bi-criteria problem. So you have here the complexity of the simplification as criteria, and the epsilon as criterion. And this is then you could say a true approximation in terms of epsilon, in the following sense that, so you give me an epsilon, and now the path that is computed by this algorithm has complexity at most twice the optimal solution for the case that epsilon would be half the size. Yeah, so which means that in terms of, if you just see it as an approximation in terms of the complexity for a given epsilon, it can be arbitrarily bad, but this is really stated as I give you an epsilon, and the output will have a complexity which will not be worse than what you would have gotten if I would have given you half that epsilon. Okay, so and the algorithm works as follows. So we have again this polygonal curve, and let me, as notation, because we will use it a lot, delta pi pj will denote the Fouché distance from pi between the segment pi pj and the subcurve between pi and pj. And this is now the algorithm. So it starts, it's a greedy algorithm, it starts at the beginning. And what it now does, it tries to quickly find a j. So initially I is 1. It tries to quickly find a j for which, if I look at the Fouché distance between pi and pj, that is smaller or equal epsilon. But if I look at the next one, that one is then larger than epsilon. And as soon as I found such a pj, I will take that segment and continue from pj. So that is written here. So I'm going to take whatever I found so far, and now I'm going to reset I to j. So I restart my algorithm to whatever I was able to go to. So it's a greedy algorithm. So what I would here, for instance, do, I look at I try to find a segment where the distance, where the distance, the Fouché distance to the subcurve is small, but then I also look at the next one and that one should be large to accept the segment, and if that's not the case, I will continue looking, and as soon as I have one, I continue from J. And just as a reminder, so for Cauchy distance, I mean the problem that we're now going to need to solve for one subcurve is essentially one row of the free space. So if I give you the subcurve that I'm interested in, then and a segment, then the segment is on this axis, the subcurve is here. I want to know, is there a path from the lower left to the upper right? And this we can simply do in terms of the complexity of this free space, which is order of J minus 1. Now the difficulty is we want to find the J such that so that this is still a valid segment, but the next one is not valid. And if we do it naively, this will take quadratic time. So then we haven't. We have one a little bit maybe, but not really much. So the question really is how can we speed up? How can we quickly find such a value of J? And an important observation or note here is that we just want to have any such vertex. So it doesn't need to be the first, it doesn't need to be the longest. I just want to have any vertex with the property that this distance is small and this one is large. And now, maybe the natural first idea might be to do a binary search to find this epsilon. That obviously doesn't quite, so you have to be careful because it's not a monotone criterion, but the larger problem is actually if you do a binary search, it might be that the J that you're looking for is very small, but you might end up doing a huge calculation if you already in the first step compute the Cauchy distance between the first vertex and the middle vertex, because there you already spent linear time. And if your binary search then goes to smaller and smaller intervals, you at the end just found a very short segment, and so you make very little progress but already spent a large amount of time. So therefore, the approach here is to first do an exponential search and then a binary search. And I have an illustration of this. So what we do is we start at pi, we first test the next vertex, then we go to the second one, but then exponential search means we then test the one 4 away, 8 away, and so on. So, and always test whether, so the test that we are performing is whether this distance is larger than epsilon. So if after performing these tests, what we have is we have an interval, and depending on how often I did this test, so this is how often I did it, it will be between I plus 2 to the k minus 1 to I plus 2 to the k. But since I always tested whether this is larger than epsilon and stopped as soon as it was, I know that at this point the distance, here I have a point where the distance is smaller equal to epsilon. Here there is a distance where the distance is larger than epsilon. And now I'm going to do a binary search on this interval. So this one is smaller equal to epsilon, this is larger than epsilon, and that means we can now here do a binary search. If the distance is smaller equal to epsilon, I'm going to search to the right, otherwise I go to the left. And okay, let's say I went to the left, then I continue, and eventually I will have found a Pj with distance smaller equal to epsilon, and the next one is distance larger epsilon. So if you naively look at the running time here, so you have log n iterations here and log n operations here. So if you're not careful, you get n squared log n running time. But if you take into account essentially, so what you have to take into account is that if you got far with your exponential search, you will also, your segment will also go at least to the, let's say, to this left boundary of the interval where you did your exponential search. So the segment will go up to there, which means that if the operations that you do are expensive, you're also making a lot of progress. And this is the advantage of doing this exponential search first, because if you would only do a binary search, you could have a very expensive operation with doing little progress. But now we know if it's expensive, we do a lot of progress, and if we sum up the terms appropriately, we see that this one's in n log n time. So we now know that this algorithm is efficient, but we do not actually know anything about the quality of the algorithm yet. So let's do the analysis of that. And an important observation here is that if I have a long segment here and I have a nested one here, so this goes from an I to a j, which is between L and M, then the distance from this segment to the subcurve, it can be worse than the distance from this segment to that curve, but not much worse. So more specifically, if I look at the delta for this segment, it can be at most twice the delta for this larger segment. And the argument here is if this one has, I look at essentially the parameterization that gives me the delta for the longer one. Let's call that one lambda. So lambda is now the value for the Fouché distance from the long segment to the subcurve. Now, this alignment in particular also aligns this subcurve with part of this larger segment. So maybe with a part starting at some qi and some qj. And what I now have is that the distance for the subcurve here from pi to pj to this qi qj, that is at most lambda because it's part of the calculations and what is represented within the larger subcurve. What I also now have, so now I'm just focusing on this part. What I also have is that the distance from this subcurve here to this segment is at most lambda, and the reason for that is that both of these are segments. So if this one had a small distance to this here, if I drop parts here, then it only decreases the distance. So let's show that. Look at this more carefully. It's actually a very simple argument. So this segment to this part had a small distance, at most lambda. Now obviously we're looking at Fouché distance, so the Fouché distance will at least align the first 2 points. It will at least align the last 2 points. And if everything in between is a line segment, which we have here, line segment, then the distance, the Fouché distance, will be actually determined by the larger of those 2 distances. And therefore I know that the distance between these 2 line segments is at most lambda. And then we can use triangle inequality, because now I know that the distance from this segment to the subcurve is at most the distance from this segment to this segment, and then plus the distance from this segment to that subcurve. And since both of those distances were smaller than lambda, my distance from the subcurve to the segment is at most 2 lambda. So that is essentially the key observation, this lemma, to see that the algorithm is correct. And we can now use this to argue some kind of greedy stays ahead proof of of the statement that the greedy choice here is at least as good as the optimal choice for epsilon half. I should probably finish soon. So let me just sketch this briefly. Let me go to the interesting part. So essentially what we want to argue is that the greedy strategy stays ahead. And the way we see it is we can argue by contradiction. So let's say up to here the greedy strategy after a certain number of steps is here, and the optimal strategy, but now the optimal simplification, but now for epsilon half with the same number of steps is here. So let's assume that the optimal segmentation for epsilon half can make more progress than my greedy choice. What I then get is that the segment from here to, so this is the case, which we are now assuming, the segment from here to the next vertex on the optimal one for epsilon half nests the segment from where the greedy strategy was to not only the next vertex, but also the vertex for which we had a distance larger than epsilon. But from here to here, I know the distance is at most epsilon half. From here to here, I know the distance is larger than epsilon, but that contradicts the previous lemma that this is at most 2 times the distance up to here. Okay, so let me wrap up what we've seen here. So we get an approximation. No, we get the greedy algorithm gives us an approximation in terms of epsilon. These are the algorithms that I showed to you. So this is frequently used, and that's why I mentioned it. This is is a very nice framework where you can also plug in other distance measures, but it's fairly slow. And this was a fast approximation if you want to use a Fouché distance. I would like to briefly talk about lower bounds. So obviously, if you want to compute the shortest path graph, we will not be able to avoid quadratic time. And we have also shown that if you go to sufficiently high dimension, you cannot do better than quadratic time. Again, this is under the strong exponential time hypothesis. But it is interesting to know that in 2D, if you have, if you're looking at polyhedral distance measures, then you can actually get a subquadratic time, subquadratic time algorithms. But that is for polyhedral distance measures. So for the Euclidean case, that's still open. Now, just a very quick. Let me just very quickly show you why there's a quadratic lower bound. So this is again orthogonal vector problem as we had the last time. What we now do is we simply have one set of orthogonal vectors placed somewhere on a unit cube here, and then we use one extra dimension to place the other set of orthogonal vectors in a unit cube here. And then my input trajectory starts somewhere, it goes to all of these points, it goes to some checkpoints here, and then to all of those points, and then back to where it started. And if there is a pair of orthogonal vectors, there will be a simplification where I can go to the corresponding vector here, then pass all of those checkpoints, so immediately have a segment to the corresponding orthogonal vector here, and then go to the end. So by seeing whether there's a simplification with 4 or 5 vertices, I can see whether there's a pair of orthogonal vectors. And this is just to illustrate this in 1D. So imagine, so here I have my 0 line, this is 1. So, and this is my checkpoint. So if I have 2 zeros, then the checkpoint is close enough to the segment. If I have a 0 and a 1, this checkpoint is still close enough to the segment. If both of these are 1, my checkpoint is too far away. So that's a basic idea of this reduction. And there has been very recent progress on lower bounds on this problem and related problems. So Brinkmann and Chaudhuri, so a PhD student of him, I think, they will have a paper at Sausage this year, which for one tackle this a kind of different variant where I'm restricting to vertices, but I'm not restricting to the fact that the corresponding segment should correspond to exactly that subtrajectory. So that's a global Fichet version. So they show that this can be solved in cubic time. And they show for many variants that you have a cubic lower bound. And maybe interestingly here they use not the orthogonal vector problem as such, but something that's called, it's quantified orthogonal vectors. So you have for all exists, which means you have 3 groups of vectors, and for every vector in one group and for every vector in the second group, you're asking, is there a vector in the third group which such that this triple is orthogonal? And that covers, so for the L infinity norm, the quadratic bound that we showed was already optimal, but this, for instance, now gives you also an optimal bound for the L1. If I'm measuring distance with L1. L2 is still open, and you can look at their paper to see why L2 is seems fairly difficult to solve, but it's an open problem. Let me just skip over this now. We already discussed it briefly. What happens if I want to add time? Then I can look at the trajectories in 3D. There are also different settings like streaming algorithms that you could look at. Non-vertex constraint simplification. There's kind of this seminal paper by, they solve lots of problems in this paper, and essentially most of the problems you could ask for non-vertex constraint simplification. You could also look at other topological constraints, so there is still kind of a lot of questions that you can ask about simplifications. Here's some lists that I made, but maybe I can talk about some of these later in the open problem session. Good, that is all. Thank you.
So questions?
I think there is a problem with the definition of error measures when we simplify the initial path. For each shortcut, we consider the error of that chain compared to this shortcut.
Yes.
And it's not important how many times we go forward and backward along this chain compared to the shortcut.
Yes.
But when we go to subsequent shortcuts, it's important when inside the initial path we go backward, for example, up to the previous shortcut, and we consider this as a bigger error. If we consider this globally, it may be reduce a better error.
Yeah, so you're addressing actually 2 issues in your question. One is the use of the Hausdorff distance here. So if I already just look at if I just look at one shortcut, then if I use a Hausdorff distance, I'm allowed to, this is my epsilon in principle. So that's kind of the similarity that I would like to have. But I can, my subtrajectory can do things like, I can go back and forth like this, which is a very strange, this does not look epsilon similar to this original one. And that's an issue of the Hausdorff distance, and that's avoided if in this other setting where we say we want to have the Fichet distance, because the Fichet distance, if I take the Fichet distance from this segment to the subtrajectory, this already kind of incorporates that I'm not, so if I would want to go back here, the amount of what I can go back relates to epsilon, so I cannot go back and forth like this, but more or less will have to move forward. So that is this one issue, which is the issue of the Hausdorff distance, which is solved if you use Fouché distance. A second issue that might have been in your question is, I'm now doing this simplification, so now I know this is similar to that segment, but maybe I could use fewer segments if I overall look at the curve and overall look at the similarity to the other trajectory. So that is a setting of, so for one, that is a setting of global versus local, where I would argue, if you will constrain yourself to vertices, it also makes sense that it should be similar to that subtrajectory. But if you are different opinion, then that global one also works. But if you now use this in clustering, where it's important that actually this is a tight simplification, I would argue that instead of constraining to vertices, what you really are looking for is just any curve with, let's say, at most k vertices that is close to my input, but then also doesn't necessarily use data points.
Then if we use, for example, Hausdorff error measure, the global error is always smaller than local error. When we minimize the error of each shortcut.
Yeah, so
consider it globally, it may be.
Yeah, so I think using Hausdorff distance with a global perspective is probably a fairly, no, I would say a bad idea. I mean, you might get very sparse simplifications, but I would argue that you would then really might end up with trajectories which now are in no way similar to your original trajectories. I mean, just examples where a trajectory goes back and forth a lot. Now, globally, using Hausdorff, you can represent it by this. I mean, maybe this is what you want to have, but then this doesn't really capture much of it really just captures the locations and not the path.
Okay, I guess we do not have time for any other question. If you have further questions, please come to Kevin after the talk. So I have an announcement. We're gonna take a school photo in front of the entrance of the university. By like 10 minutes from now, so please, before going to lunch, go to the main entrance. We want to take a photo if you want to be in that photo. So that's the main announcement. And after that, we go to lunch.